This is our final video talking about attractive forces in section 8.4. In the last part, we talked about stronger forces of attraction between particles, and now we're ready to focus on the weaker forces of attraction. Weaker forces are temporary attractions that exist between neighboring particles due to temporary or permanent partial charges, such as those del plus or del minus that we've been writing on our molecules. The attractions are usually indicated in diagrams using dashed lines. You can see that in this diagram to the right. Notice that the strong bonds that exist between hydrogen and chlorine in this diagram are drawn with solid lines because those stay connected unless chemical reactions are taking place. But the dotted line here indicates a much weaker attraction, the intermolecular attraction, meaning attraction between separate molecules that can occur. These weaker forces of attractions also vary in strength depending upon the identity of the substances involved, and this strength is indicated by how much energy is required to break that force of attraction, break that temporary bond. This is a diagram that summarizes what we're about to talk about. It shows the weaker forces of attraction. We have 4 different types that we're going to look at: ion dipole, dipole-dipole, hydrogen bond, and London dispersion. Let's start with ion dipole. Since an ion is involved in the ion-dipole interaction, these attractive forces tend to be stronger. It can take from 40 to 600 kilojoules per mole to break these bonds. What we see here is a water molecule. There's also an anion. And if you recall, water is a polar molecule. It's a dipole. In that particular molecule, the hydrogen ends, shown here in red, have a slight positive charge, while the oxygen end, shown in blue, has a slight negative charge. And you'll notice as that anion is dragged closer to and farther away from the water molecule that the water molecule responds to its presence. As the anion gets closer, the water molecule did feel the force of the attraction to the anion, and so the hydrogen end always turned itself so it was nearby it, so that the hydrogen end was pointing towards that anion. Another weak force of attraction is dipole-dipole interactions. These attractive forces are significantly weaker because they only have partial charges on those molecules, ends that are slightly positive and slightly negative. There are no fully charged particles, such as ions, involved in this particular type of interaction. In these molecules, the different colors of the molecule indicate the different positive versus negative nature. The yellow that you see indicates these temporary attractions between these particles, and you'll notice that they do have some effect upon each other, but it's not a strong effect. It's not a strong bond that holds them there, so that's why it's easy for them to break and easily move away from each other as they're moving along. Now, they only require 5 to 25 kilojoules per mole to break these dipole-dipole attractions. The amount depends upon the size of the partial charges. Molecules that have a larger dipole are going to be harder to break apart, and it's going to take more energy. While dipoles that have very weak dipoles, those would have only weaker attractions and would require much less energy, maybe down around 5 to 10 kilojoules per mole to break those attractions. Here we can see that these electron clouds are kind of centered more around the green atom than the blue, so these are definitely dipole molecules. Okay, and you'll notice that they do line up so that the green end that's negative on one molecule is going to be nearby the blue atom on the other molecule, because that is the side with slight positive charge. Now, hydrogen bonding is also a weaker force of attraction. It can take from 10 to 40 kilojoules per mole to break these bonds. Be careful. Hydrogen bonding does not refer to the hydrogen-oxygen bond within one molecule, or the hydrogen bonded to anything within a molecule. When hydrogen is attached to a highly electronegative element, something such as oxygen, nitrogen, or fluorine, then it has a fairly strong partial positive charge, and that makes the molecule a larger dipole. So when these molecules come near each other, they can hydrogen bond, which means the positive end of, that is the hydrogen on one molecule, will be attracted to the oxygen, nitrogen, or fluorine atom on another molecule because that end is strongly partially negative. So for water, being a mid-range dipole, it might take from, maybe around 20 kilojoules per mole to break those bonds. Now, one of the most common substances that forms hydrogen bonds is water, as we just looked at. And we have a video here to look at it. If we take a closer look at water, zooming in on the water that's in this beaker, here's what a water molecule looks like. Recall that it has partial positive and negative charges on those different ends due to the polar bonds, the polar OH bonds. And that's going to allow these water molecules to hydrogen bond with each other. When you see a dashed line form, or a dotted line in this case, that's indicating that we have a force of attraction here. Now in reality, these would continue to move unless they were getting frozen into position due to cold temperatures. So these are weak bonds. But if this substance does freeze, then you can see that it freezes with a much more open structure, and hence, as we said before in class, water, when it freezes, its solid form, ice, is less dense than its liquid form because of that extra space left in those crystals that are forming. Now, the weakest force of attraction that can occur between particles in a substance involves something known as induced dipoles. Substances that don't normally have a dipole, such as this spherical atom shown at the upper right. The dot indicates the location of the nucleus, and you can see that the electron cloud is symmetrically spaced around that nucleus. If that atom approaches an ion, such as the one shown down here on the bottom picture, that's a positive ion, so if it approaches that cation, then it can induce a dipole, causing the electrons in that cloud to kind of move more towards the left end of the cloud, creating an electron cloud that is no longer spherical, but is kind of elongated, and it now has a slight negative end and a slight positive end. But this will only exist as long as that atom is nearby that cation. If it moves away, that dipole will go away. So the cation is inducing a dipole in that atom, and it's only temporary. Induced dipoles can exist in atomic substances like xenon, such as what we saw in the previous slide, but it can also exist in molecules. As a matter of fact, larger atoms or even larger molecules can have larger induced dipoles because they have more electrons and their electron cloud is larger over the entire atom or molecule. Therefore, that electron cloud is easier to deform. If we look at this picture over here, we can see that the original molecule looks like this. This is iodine. It has equal sharing of electrons. But when you have iodine molecules near each other, if something causes one of those clouds to deform, and so you end up with slight positive and slight negative ends, then that can induce a dipole in the neighboring molecule, which can induce a dipole in its neighboring molecule, and soon you have a lot of molecules that have induced dipoles. But once again, these are temporary. They appear, but then they quickly disappear again too. As soon as whatever caused the dipole, whatever induced the dipole is gone, then it'll go back to looking like the original iodine electron cloud. We actually have a name for the forces attracting induced dipoles. They're called London dispersion forces, and they can require between 0.05 and 40 kilojoules per mole to break. So these can be some of the weakest. If you have a very large molecule or extremely large atom, then you might have a value that's closer to the 40. If you have a very small atom, then with a very small electron cloud, it can't deform as much, and so it's going to have a London dispersion force down around the lower end, 0.05 kilojoules per mole. So here's an example where the one on the left has induced a dipole in the one on the right. We can see the dipole starting in the left molecule, and because the partial negative charge is on the right side of that left molecule, you saw that the partial positive charge ended up on the left of the neighboring molecule, so that you'd have opposite charges near each other for attraction purposes. If we replay that, as the electrons are moved towards the right side of the molecule on the left, it's going to repel the electrons in the left side of the molecule shown on the right, and therefore you have an induced dipole there as well. So these London dispersion forces are weaker forces because induced dipoles are only temporary. They don't exist for long, but they can form and reform and go away very quickly. So they arise from transitory dipoles. So you can see that they can switch directions back and forth, and things may not be existing without a dipole for very long before another dipole is induced upon a particular molecule. That's the end of Chapter 8. I hope that you found these videos helpful, and be sure to ask me in class if you have any questions.